Can you hear me? Yeah, okay, good. It is my pleasure to introduce the first speaker, Professor Max Welling. So Max is a professor of computer science at the University of Amsterdam and a co-founder of CuspAI. So Max has led many innovations in AI, and he has influenced, I think, many of us. Examples are variational autoencoders, equivariant neural networks, stochastic gradient longitudinal dynamics, graph neural networks, and many more. Max has also applied his innovations to impactful problems. He has worked in several industries. He was formerly distinguished scientist at Microsoft Research and VP at Qualcomm. So it's my great pleasure today to introduce Max to talk about machine learning for molecules and materials. And he's currently indeed leading this new initiative, a new company, CuspAI, where the goal is to transform material discovering using AI for impactful applications. So thank you very much, Max. Please go ahead.
All right, that worked great, and this works great. Thank you, Roberto, for the nice introduction. Roberto is an old friend, I would say, and a colleague of mine, and we've done many interesting projects together, both at Qualcomm, but also outside of Qualcomm. And you'll see one example really flashed quickly up today. It's a great pleasure for me to be here. In fact, this institute is, I've just learned exactly, at the interface of the sciences and the machine learning, which is very deeply at my heart. This is exactly where I work and where I'm most excited about. So let's start by something that I feel is very appropriate to talk about here in England or in London, which is the Industrial Revolution. I guess it started here when people started to understand things about thermodynamics. And thermodynamics will play an important role in my talk today as well. And so the Industrial Revolution was all about replacing physical work or human work with physical work in terms of machinized work. And now sort of that led, in a century to the information revolution or the digital revolution in which we find ourselves now. And so that's the revolution of AI and transforming the world through smart systems, and it's about information or level of organization. And the key player of my talk will be the free energy, which you see there, which is given by the energy minus the entropy. And the energy symbolizes the Industrial Revolution, which is replacing physical work, and the entropy term, which is the lack of information about a system, symbolizes the information revolution. And it's kind of interesting that, of all people, Steve Jobs knew about the free energy, and he wrote that this revolution, the information revolution, is a revolution of free energy as well, but of another kind. It's free intellectual energy. And that turned into this. So this is how modern AI has advanced. These are already a few years old, advanced to produce images of very high quality. Nowadays, we've moved on to multimodal data. We've moved on to videos. And in fact, of course, you know that quite recently OpenAI came out with sort of a artificial scientist. And I used to joke when I gave these talks that the professors was the last job that was going to be replaced by AI, but I'm not so certain anymore about that, given that we now have, a pretty good research scientist, artificial research scientist. Of course, it's a tool still, but things are moving incredibly fast. Now, videos of dogs playing in the snow is nice to look at, but it's not what gets me out of my bed every morning. It's these types of applications of AI which I find infinitely more exciting. And here we see a few examples. Of course, one is AlphaFold, which I guess was developed here in London as well by DeepMind. There is a video, I'll talk a little bit more later, is how to generate molecules by prompting them with certain properties in your computer. And there's, of course, the project by EPFL and DeepMind on keeping a plasma stable inside a nuclear fusion reactor. Now, I want to argue that there is a disruption happening in the field where machine learning is disrupting the sciences. And in the same time, the sciences are also contributing to the development of better machine learning algorithms. And so I would sort of explain this disruption in two steps. And the first step is that, we are going from experiments in test tubes in the real world, which will always remain important, by the way, don't get me wrong. But they're also expensive and slow, and this slows down the design process, the engineering process of coming up with new, let's say, molecules or materials, or airplanes for that matter. And so in the old days, the only thing that people really could do is just, they didn't have computers and they just tried a lot of things at random. They put chemicals together and they observed what the properties of it were, and then they tried again. They tried to learn something and then they tried again. So later, this of course became far more data-driven in the sense that people would do lots of experiments, but then they would record all the data that came out of that, with fancy measurement devices into a computer, and they would store it in databases, and they would have machine learning algorithms maybe to find patterns in that data and come up with better hypotheses. So these days, I would say what's happening is that not just these experiments, the outcomes of these experiments are done in a computer or stored in a computer and analyzed. These days, we're actually analyzing the physical system itself. We are running the laws of physics in our computer. So instead of having nature do the experiment, we now do these experiments, some of these experiments in our computer. And that cuts down a lot on the cost and the time for development. But of course, it's very expensive and you need a huge amount of compute power. But fortunately, Moore's law is still active, and so this exponentially becomes better. And of course, AI, as I will argue, is going to play a key role in accelerating this forward. So that's the first step of that process. That's going from experiment to simulation. And then the second step is going from simulation to emulation, and I will also give you some examples of that. So what do I mean when I say from simulation to emulation? So imagine you're a car manufacturer and you want to design a new car. Now you've already subscribed to the previous step, which is I'm not going to do the actual wind tunnel experiment in the real world. I'm going to do the wind tunnel experiment in my computer. So this is possible now. You just simulate Navier-Stokes equations in your computer, and you just analyze the hydrodynamic properties of your car. Is it the aerodynamic properties of your car? Will it be a fast car? Will it be energy efficient, etc.? But then the next generation of car comes around, and instead of doing the same thing again, you would now have stored all the data from that simulation in a big database, and then you would have trained a neural network. And the neural network can do a number of things. It can either predict the outcome of the experiment directly. It can just look at the car, at its features and say, this will be a very aerodynamic car. That's a stretch. It's hard, but people try that. The other way in which you can impact the simulations is by actually accelerating the actual simulation there in your computer. And so I will give you an example in a minute about how that has happened for weather prediction. So you can actually, this is typically a partial differential equation that you have to run, it's a Navier-Stokes equation or some variant of that. That's done by numerical integration. Mathematicians know all about that. That's a field that's 100 years old or more. But what people have done now is if you have enough data, you can actually train a neural network to simulate these equations forward. And there's been due skepticism about this, of course, and some of it is good. But I'll also tell you a story how this has really changed the field of meteorology. And so the application of machine learning to the sciences basically happens at this point across all spatial temporal scales. It goes, if you talk to particle physicists at CERN, there's groups that apply machine learning to analyze their data from LHC, all the way at the femtosecond picometer scale. And then you go through sort of chemistry, maybe condensed matter physics, which is about molecules. That's sort of at the cusp of where quantum and classical sort of move into each other. Then there's fusion of plasma physics, fluid mechanics, geophysics, all the way up to astronomy and astrophysics, which is at the scale of the entire universe. And of course, all of these are typically described by PDEs of some kind, or ODEs, or collections of ODEs, of SDEs. Some of these methods which basically, if you have something that's continuous, or if you have something that is causal, you'll very quickly, or local, you very quickly end up with PDEs, for instance. And so I'll talk a little bit about some things that have happened in this field of fluid mechanics and some things that have happened in molecules in light of what I just described. So this is, I would say, a disruption that started to happen, maybe 4 or 5 years ago. Some of the earlier papers, and what happened was basically, in meteorology, there's a huge amount of data available in the order of petabytes. So the meteorologists have been very, very good at storing their data, and that's paying off now. And so computer scientists and AI researchers have then taken that data and trained actually a very dumb model. So it's not a model that looks at any physics, which might be a little disappointing. It was disappointing for me. But if you have so much data, apparently that's no longer necessary. And so it's a big transformer of some kind that predicts the future state of the weather, basically, of the atmosphere, I should possibly say, because it's temperature, pressure, wind speeds, lots of other properties there. In a future time, up to 10 days, forward in time, just like typically numerical weather forecasts do. So the first one was this FNO paper by NVIDIA, and then there was a paper from Huawei, Pangu Weather, which was actually very, very good at that time. And then paper by GraphCast from DeepMind, and then lots of other papers that came after. So I'll tell you a little bit about the model that we sort of trained at Microsoft Research. I was involved in this. It's called the Aurora model. So this model is different from the others in the sense that it takes in very different data sets. So it can take very high resolution data that's local maybe to the United States and Europe, and very low resolution data that's completely global, different data formats, all sorts of data. It's all being taken in by this architecture called a perceiver. The perceiver encodes all that data into some latent space of a fixed dimensionality, which is typical of what happens for encoder models. And then there is some dynamics model that predicts the future state of this latent space. And then from that latent space, you then predict all the atmospheric variables at the time that you're interested in. Of course, there's a lot of details I'm skimming over here. But it's very important that it's able to get a huge amount of data encoded and trained on. And this is about over 1 million hours of data. So the method predicts about 5,000 times faster the weather than IFS numerical forecasts, which is the standard in this field. And if you look at the graphs down there, you see that you could argue it's better than the IFS forecasts, or at least as good if you're a bit skeptical. But it's certainly not worse in these forecasts. That's for the usual things like wind speed error and surface temperature error. But we found you can actually very easily fine-tune these models to predict other things as well, like air pollution or concentration of greenhouse gases, or an accurate 5-day global air pollution forecast. All of these things can actually be predicted with this model. And it's especially this air pollution that got some people very interested, and meteorologists quite interested in these models. So I want to emphasize that I think this is truly disrupting, because this happened over 5 short years. The meteorology is like a century old, like it's a very old field. And I have seen meteorology offices, like literally working with them, go from extremely skeptical, this is never going to disrupt 100 years of research in sort of numerical analysis, to a little panicky. This is actually, when they started to test these things themselves and figured out they actually work really, really well, like, okay, we need to get ahead of this and integrate this in our forecasts. So I would say this is what a disruption is about. It's something that goes very quick. Many people are very critical, skeptical about it, but figure out at some point this is actually disrupting our field. And that's where we are now. And of course, it's still going very fast, right? It's still improving very fast. The other field where this has happened is in chemistry. And so it's sort of apt that we're here in the chemistry building. And I want to talk to you a little bit about molecules. So maybe, I don't know if there's chemists in the room here, but this is, of course, for many people, not too difficult, but it's like an atom consists of atoms, a molecule consists of atoms. They are bonded in some way using different kinds of bonds. I've shown here the covalent bonds. Those are strong bonds. And this molecule will evolve over time. And it's sort of two theories combined that, that determine how it evolves. The first one is just Newtonian mechanics, like 16th century old physics, that basically, for every atom, it computes what are all the forces on this particular atom, and then it moves it, computes a velocity field, and then moves the atom exactly by that velocity, right? So just Newton's equations. Now, this thing is, however, extremely chaotic. So the theory of chaos and nonlinear dynamical systems applies, which means that it's very hard to predict the actual path very far into the future, because you would need the initial conditions infinitely precise, and you don't have that. That's also why the weather, after 10 to 14 days, there's a wall. You cannot predict beyond that without starting to use probability distributions. The problem with this is that there's actually another theory which is really important, which is the theory that describes the electrons, which sort of are a cloud around this molecule. And the electrons are so light that you must describe them by quantum mechanics, otherwise it doesn't make a lot of sense. And so in order to compute that force on the atoms, you will have to solve the Schrödinger equation. And if you have like 100 or so electrons, this is completely infeasible if you want to do it exact or with very high precision. And so people have come up with very good approximations called density functional theory, which is often called ab initio methods, which are an approximation to solving quantum mechanics, but are still very, very slow. And this is where machine learning has also played an important role, is in replacing that quantum mechanical calculation by a neural network. And that's called a machine learned force field. So molecules are truly important to understand and be able to simulate, because they are at the core of many of the problems, engineering problems that we have, and also societal problems that we have and need to solve in the next 40 years or so. Of course, molecules are at the core of drug discovery, solar cells, lubricants. I think it's something like 20% of all energy gets wasted by basic friction. Catalysts, really important as well. Nitrogen fixation to get fertilizers. And carbon capture, which is the field I'm very excited about, because climate change is going to hit us, and we will need, as part of a solution, we will need to start getting carbon out of the atmosphere. At some point, in fact, after 2050, we need to go carbon negative in order to stay on track with some of the sort of 2-degree global warming targets. And we have to stay negative for 50 years or so. So the only thing you can do is capture carbon out of the air, out of the atmosphere, and store it. And so machine learning has been impacting these sort of physics and chemistry fields at almost every level of resolution in terms of spatial temporal scale. At the very bottom level, there's quantum neural Monte Carlo. These are methods that try to sort of approximate quantum mechanics at a very principled level. Then there's quantum density functional theory, where there's now machine learned functionals that are being trained. Then there's these force fields. So you go up in this ladder, and it becomes more and more coarse and more approximate, but also faster and more efficient, right? And then there's machine learning potentials derived from particle-based simulations, and then there's machine learning potentials derived from coarse-grained particle-based simulations. And if I have time, I'll talk a little bit about classical density functional theory, machine learning potentials, which is something that is not quantum mechanical, but tries to describe fluids using density functional theory, and then all the way up to, the PDE surrogate models, which you just described for the atmosphere. And here's sort of a little bit of a summary of sort of some of these things that I just described. On the far left side, you'll have a beautiful simulation or a beautiful visualization of the Schrödinger equation. This is from Quantum Magazine. And so this green cloud is the electron cloud. And it sort of oscillates around the atoms of the molecule. I find this very beautiful because you sort of see that the energy is conserved and it just keeps oscillating back and forth. And that's the electron cloud. And then, so there's density functional theory and quantum variation of Monte Carlo. Something called Fermi net and Pauli net. You may have heard of it, but that's two innovations that happen at this quantum variation of Monte Carlo level to solve the ground state, for instance, to compute the ground state of a quantum mechanical system. So when you go to the level of molecules, you have the Langevin equation, and there are these force fields, these machine learned force fields, which are really starting to revolutionize this field. So you can do these MD simulations much more accurately, much faster than if you would have to go using quantum mechanics, for instance. Then there is this classical DFT, which is some theory about fluids. I can talk about a little bit more if I have time. And then there is this Navier-Stokes equation and solving it with PDEs, solving it with machine learning. And I talked about ForecastNet, GraphCastNet, Aurora, etc. And then at the bottom, there's some applications. There's there's something I will briefly talk about on the far left, which is drug discovery, which is generating an actual drug molecule in the pocket of a protein to then function as a drug, which is also a very fast developing field. And then there's, of course, catalysis. Meta has been very influential here in generating lots of data. Also, machine learning models are predicting how molecules will adsorb to the surface of a catalyst. And then material science and materials discovery. Some recent papers, for instance, by Microsoft called MetaGen, that generate materials with prescribed properties in a computer. Okay, I'll switch gears a little bit now, which is I'll talk about how. So this was how machine learning is influencing the sciences. Now I switch to something else, which is how mathematics and physics has influenced machine learning. Sort of this is through symmetries and equivariance, and it's very important for chemistry because if you think about a molecule, you try to predict properties of that molecule that typically don't depend on where this molecule is in space or how it is oriented. And so you want to build in these symmetries, that it shouldn't care about its orientation and location. Now this is what the physicists have been doing for a long time, building symmetries in their theories. They say the theories must be covariant under transformations, which basically mean the same theory should apply in the same form if you change from one observer to another observer. This has led to, for instance, the insight that electric fields and magnetic fields are really two sides of the same coin, and that can be transformed into each other by having an observer that moves with a certain speed relative to one of these fields. It has also led to the full theory of general relativity by noting that acceleration and gravity really are two sides of the same coin. They're connected by a symmetry, if you wish, they're the same thing. All of that leads then to basically general relativity. And in fact, the entire standard model of elementary particles is organized through its symmetries. You can map certain neutrinos and other neutrinos by a symmetry group. So there's U1, SU2, and SU3 symmetries in where these particles are being transformed into each other. Okay, so then the question becomes, how can you use it in a neural net? So the sad thing about a neural net is it doesn't know about the symmetry. So it feels normal that if you take an input and you rotate the input, you should understand that that's just rotated version of the same input. But it will treat it as a completely new thing, and it will have to train. If I take a cat and I show it to you upside down, it's still a cat, right? You know that's still a cat. You don't think about it. But the neural network will have to see it as a completely new object, and also learn that that's also a cat. But if you tell it that things that are rotated or transformed are actually the same thing, you can hard code this into your neural net. Then it doesn't have to relearn that. And here's two key students that I worked with, Taco Cohen and Maurice Weiler, but many other in my lab. I've worked on this, who have actually developed this theory of equivariance in neural networks. And the idea is basically that if you look at this, you can quite see where I'm pointing to, but there's this bottom plot there. There's a lizard or a gecko, and if you translate it in the image and then convolve it, you get to the right bottom image. Or if you first convolve it and then translate it, you also get to that image. And if that diagram closes, you can say that you've been successful in building in that symmetry. So now the neural network understands this particular symmetry. And you can, there's a whole theory of how to do that. And if you're interested, you can read that book. It's free and online, but you can also buy it as a hardcover. And it's beautifully illustrated, and it's a great introduction to learn about equivariance. So with these folks, with these students, we've applied this to molecules. So of course, we first had to think about how to actually do machine learning on graphs, because a molecule is not a neatly organized grid of pixels. And so you start thinking about how do you do message passing or convolutions on a graph. So I did there with Thomas Kipf. Then we build in equivariance in these graphs, which means that if you rotate the graph and do convolutions, or first convolve and then rotate, it should be the same thing. That's with Victor and Emil as well. And then on the right-hand side, you see the updates. They're actually not so hard, right? It's not like a massive, complicated, algorithm. It's actually not a very difficult algorithm, but that algorithm gives you the EG and then updates, which give you these graph message passing updates that keeps the neural network aware of its symmetries. And then I think, so this is the second revolution I want to highlight, where machine learning has made an immense impact in some scientific field, and it's still ongoing. In fact, I'm involved in collaboration with Meta to build a very sort of comprehensive foundation model across all of the sciences. And there's people in Cambridge, like Gabor Zani, who's also working on that. He has developed MACE. He's at Cambridge, and there's a lot of development in this field. So this is from a paper by the person, I think, Klaus Robert Müller and his team, who were maybe the first who actually thought about applying machine learning to these force fields. And so you get some idea of that. There's just three things you can do if you're faced with a molecular dynamics simulation. For very small molecules, you can do this DFT level quantum mechanical calculation. It's very exact, very accurate, but very slow. On the very right-hand side, you can use what's called sort of force fields. These are sort of like Lennard-Jones type of very simple force fields. They're very fast, but very approximate. And you can apply them to rather complicated molecules. But now what's happened that in the middle, this machine learning force fields have happened. These are neural networks that predict the quantum mechanical calculation. They're almost as accurate as the quantum mechanical calculation, but they're thousands of times, like many orders of magnitude faster, approaching the speed of the classical force fields. So we're bridging that gap now using the machine learning force fields. And so we've also contributed to this by these SE3 equivariant architectures. You can see the citations there. And I just want to point out that this graph doesn't care about the orientation, right? However you input the molecule, whichever orientation, it doesn't care about it. And that's really what you need. Okay, so back to how did physics influence my thinking around symmetries. And so this is very, very new and very recent. We are writing up a paper now. I'm very excited about that. But so we've looked at neural networks very statically. We thought there's an input, it's static. The input then produces a latent representation. It's static, it doesn't change, it doesn't move. But we all know that life, that our input is dynamic. We reason, we solve puzzles. And in fact, when you look at the brain, people just see that there is waves happening on the surface of the cortex. And so this, started a collaboration with Terry Sinowski and Lyle Muller and my student Andy as well. And it basically tries to reproduce these traveling waves and these oscillations in the brain and see if you can use them as a neural network architecture. So it's a bit like the wave in a football stadium. And this paper just came out a few days ago, so we put it on the archive. It's a perspective on how you can use dynamical computation, we call it space-time computation, to improve information processing in neural networks. I'm very excited about this work. Another paper will come out where we actually go in much more detail on a particular model that has these waves and actually has amazingly good properties. I'll talk a little bit about that. And this is my paper with Roberto. I wanted to highlight this. This is by far the most quirky paper I've ever written. It was a lot of fun doing that. And in some sense, it was work back from the title because we needed to have something for Jeff Hinton's 60th birthday or whatever. I forgot precisely what kind of event it was, but we thought, okay, can we write a paper which talks about Hintons? Because a Hinton is, it's a particle, right? You see there's fermions and bosons and everything ends at on. So I thought Hintons, it could also be a particle. And so we worked our way back. And we actually came to a very interesting theory, I still think it's very interesting, of how you can use quantum field theory as a sort of representation in a neural network. And quantum field theory is, of course, it's quantum, and that makes it difficult to handle, but it's also oscillatory, right? Quantum fields are oscillations. They're large collections of oscillators. And so in some sense, this is also a prelude to what I'm working on now, although now I'm not doing, I need Roberto for the quantum field theory part, so I'm just doing classical now. And so the way we think about basically this classical theory of using sort of oscillations in the brain, you can think of it this way. So you start with a state of the world. Of course, the world evolves, like in the bottom row. The world evolves into some other state. But you can also encode the world in a representation, which could be your brain. And then you also need to evolve the state of your brain somehow to a new state of your brain that then predicts the future state of the world. If that diagram closes, you can sort of argue you have a generalized sense of symmetry. Of course, when this thing at the bottom is an actual symmetry, then the thing at the top must be a representation of that group. That's how equivariance works, of that symmetry group. But if it's a symmetry that you don't quite know what it is, maybe you don't know the group or the representation theory for that, or maybe you just have data, then you can generalize this idea of symmetries to this homomorphic representation, this idea that this diagram needs to close. Now, that means if you want to generalize, you have to think about what do you put there at the top level, right? So if you know it's a representation of a group, then you know how to transform things. But if you don't know what it is, you have to put something there. And what we put is basically oscillators, basically a graph neural net where the neurons that are connected together, they oscillate up and down, but they impact their neighbors. So you get sort of these traveling waves through the cortex. And that's exactly what happens. So at the bottom line, we have the world as a 5. The 5 is rotating in this case. Then we encode in some latent space. We put this prior, basically, that it's a bunch of oscillators. And then what we find is, as we evolve the state in the latent representation, we learn this to become waves in that state. And then, of course, you can decode back. And that is actually a form of equivariance, if you wish, and you can train it completely. And the representation that it follows is this kind of PDE that propagates waves. And what I thought was very interesting, so what I'm showing you here is a piece of cortex on the right-hand side where people look at the orientation tuning of these neurons on the cortex. So they say, to what direction are they most sort of sensitive. And you get these color codes, which you consider these groups, like the blue is one orientation, the green is another orientation. So it organizes itself in what's known as these topographic maps, where you get patches of cortex which are sensitive to a particular direction. And what did we find in our artificial cortex? So here is basically, we were training these models, and we would have waves propagate on our artificial cortex, if you wish. And then we looked at, okay, to what directions are these neurons now actually selective? And we find also these very interesting topographic organizations. What that precisely means, I don't know. I'm not a neuroscientist, but it seems we can sort of, this is a natural way to organize sort of the cortex. And here's another application of how this kind of idea of putting this wave prior, in some sense, on your models is very helpful. So this is a very simple RNN. On the top lines, there's the usual RNN, recurrent neural network, that maps a future hidden state to a current hidden state to a future hidden state is driven by an input. So we did some tricks, including replacing the usual matrix multiplication by a convolution and some initializations. And then when we trained, we found these wave-like patterns. So what you see here is that on the vertical axis, there's basically the neurons which are stacked. And on the horizontal axis, there's time. And what's happening in these images, what you see is, so you get a neuron that gets activated, and then over time, it moves this activation to a higher sort of channel in its stack. And it's starting to rotate. So this information is starting to rotate around. And that creates some kind of code that it can keep in memory for a long time. So it has these kind of rotating patterns that are very stable. It can keep that in its memory for a long time. And we started to test it on tests like, so there's a whole bunch of numbers as your input. When you see a 9, tick the next number and remember it. Then there's a whole bunch of other numbers again. If you see another 9, tick the next number added to the first number you've in memory. And then you see a whole bunch of things again and until you see another 9, and now output the sum of these two things. So that's a pretty hard task. And you can sort of play with how long it needs to keep things in memory. And it completely blew any other sort of RNN out of the water, because these other RNNs, their information diffuses. It can't hold on to this information. It diffuses across all of its neural states. And here, because it's sort of rotating in these patterns, it could keep it stable and nicely decode it. Okay, how much time do I still have? Right, I still have quite a bit of time.
20 minutes, I would say.
Okay. All right. So now I can switch again, and now we're going to. This is still about how can ideas from physics influence machine learning, but now in a very different way. We've talked about waves, we've talked about symmetries. Now we're going to talk about how ideas from non-equilibrium thermodynamics can influence and build better machine learning methods. And in fact, the first paper in this revolution of diffusion models that I'm going to talk about was this one from 2015. It's a bunch of physicists actually turned computer scientists. And it says deep unsupervised learning using non-equilibrium thermodynamics. So it's right there in the title that they were inspired by this non-equilibrium thermodynamics. And the idea in this picture here on this side, you can see that you start with a spiral. This is your data spiral. And then there is a process that diffuses that data into an amorphous kind of uniform or Gaussian blob. So you just think of it as you're adding noise to these points. You're adding more and more noise until it's just one big noisy blob. That's called the, for instance, one of them is the Ornstein-Uhlenbeck process. It says some Brownian motion type thing which just noises things up. And then what the model does is it monitors this process very carefully. Every step, it monitors how that happens. And it tries to train a model which reverses time. So it basically says it tries to unscramble the egg, right? So you can think of if I take an egg and throw it on the ground, that's easy. It's much harder to take an egg that's on the ground and unscramble it back into your hand, right? That's impossible if you wish. It's not impossible by physics, by laws of physics, by the way. It's just very unlikely to happen. Yet that's what these models try to do. So they try with a scrambled egg, and they try to turn the direction of time around. and produce beautiful images or videos or whatever on your screen by basically doing the inverse of the process that destroys information, right? So the top line, where you noise things, you can think of as normal physics, where entropy increases, where the second law of thermodynamics holds. And then when you go in the opposite direction, it's like you're actually, decreasing the entropy now. You're looking at the video in the reverse direction, which is very unphysical, unless you add, energy into the system at the expense of entropy somewhere else. So I was very inspired by this guy, E.T. Jaynes, who is the inventor of the maximum entropy principle, who viewed statistical mechanics basically as a Bayesian theory. He says there's nothing real about entropy or probabilities. It's just our lack of knowledge about the system, why we need these quantities, right? So in fact, it's very real. If you don't know where all the atoms are, you cannot use them in the way you may want to use them to extract, let's say, energy or work. And it's this lack of information about the details of the system which means that we sort of losing the ability to manipulate the environment, and that's captured by this idea of entropy. And here's a whole bunch of equations, and maybe some of you don't recognize them, and some of you do. Now I'll just go very carefully through them, and maybe you're on one side of this divide. I'm not sure how many physicists and chemists are in the room and how many machine learning people are in the room. But if you're from the machine learning side, you look at the left-hand side, and this basically says Bayes' rule. It says the posterior distribution over a whole bunch of latent variables, unobserved, hidden variables, z, given observations x, is given by Bayes' rule. That's simple. And then Radford Neal and Jeff Hinton wrote down in some paper a long time ago a free energy for machine learning. And that free energy, of course, the free energy I also talked about in the first slide. That's minus the log p of the data. That's called the evidence. And you can write that as the expectation of minus the log of the joint pxz minus the entropy of q, where q is it's called a variational distribution. And if you're doing inference in your system, you're trying to find the explanations of your observations through the causes or the factors that actually caused it. You have to do inference in that system, where you have to compute this distribution p of z given x. And you can approximate that process by minimizing this free energy over q. And the m step, the famous algorithm, EM algorithm, the m step is change f by changing the parameters in p. That's learning. And the e step is relaxing f by changing q, which is inference. So probably if you didn't know about this, you won't know. You will still not know about it. But if you do know about it, you recognize this as basically one of the very core algorithms we use in graphical models and machine learning. And on the other side is the perfect equivalent of that in physics and chemistry, which is now, instead of writing down the posterior distribution, we write down the Boltzmann distribution, which is the equilibrium distribution. If you give me a Hamiltonian H, which describes the energy of the system, x are observations, maybe temperature or volume or things like this, and then z are the microscopic degrees of freedom that I'm trying to think about. We write down the free energy. This is the actual physical free energy. I remove some constants like Boltzmann constant and such. There's a temperature now which wasn't on the other side, but it's exactly the same equation if we identify minus log p xz with the Hamiltonian H, and otherwise Q is the same, and we set the temperature to 1. And then work in this case is changing F by changing H. So that's the same as the M step. So we're changing the Hamiltonian by changing the free energy. That's what we call performing work on a system. And so that's learning in machine learning. And then the E step is something that's equal to the second law of thermodynamics, which is relaxing the system, increasing the total entropy of the bath plus the system. And that's basically changing Q, but keeping H fixed. So you keep the Hamiltonian fixed, but now you reduce Q. And that's inference, and in this case, it's just relaxing the system to equilibrium. And you can show that the entropy the entropy of the system and the bath jointly will always increase under that. So my point is that it's the same mathematical theory that describes both of these. And in fact, it's that theory which led to the discovery of these diffusion models, which generates videos and images now on your screen. And I'm writing a book about this, so it's a lot of work, but hopefully it will be done by the end of this year. And then, so here's then sort of, I won't talk too much about what's at the bottom here. If you're a physicist or a chemist, you recognize these things, and maybe that's the only thing that we need here. At the top line, what you see is the typical thing from a machine learning paper, which is you start with an image of a dog, and then you add this kind of diffusion model to it, and you end up with a noisy image. And then there is this learned inverse model, which takes any noisy image and then turns it into an image of a dog, right? And you try to learn this inverse model by looking at lots of examples that go in the other direction. Now, and you can now come up with all sorts of very interesting conclusions and analogies between these things, because this is literally one of these physical non-equilibrium thermodynamical systems. You can write down Crookes fluctuation theorems. If you know about Jarzynski equality, it's very, that's in chemistry, a very famous non-equilibrium thermodynamical sort of equality. It's the same as annealed importance sampling. It all maps very beautifully between these two fields. I won't go into detail because it's too much, and I don't have a huge amount of time left. What I want to point out that we've been developing a lot of theories in machine learning, including variational inference and MCMC sampling, which are inference algorithms, optimal control algorithms and G-flows, which are control algorithms. Then there is Schrödinger bridges and optimal transport algorithms, which we use, let's say, in chemistry as well. I'll talk a little bit about that. And then there's diffusion models and normalizing flows, which are generative AI models, which generate these images. And they can all be thought of as some kind of process of minimizing a free energy. And if we have Markov chains for both the encoding distribution Q and the decoding distribution P. So it's basically a large variational autoencoder, but over many levels of stochastic variables. Okay, let me just say a few things about, I'll just go a little quick here. So here is an application of these diffusion models to generating molecules that we did with this group of students. It's all equivariant, and basically you start with a noisy blob, and you turn a noisy blob into an actual stable molecule in your computer screen by looking at many molecules that you sort of dissolve into noisy blobs and then inverting that. So that's basically the equivalent of a video of a dog playing in the snow, but then actually generating molecules. The beautiful thing is that you can condition them on properties. So you can say, I want a molecule with these properties, and then it will generate these molecules. You can do the same thing for drug-like molecules that fit inside a pocket. So now you condition on the actual shape of the pocket, and then you generate a molecule that would nicely fit inside that shape. You can even fixate certain parts of that molecule because you think you know which anchors fit into those sides of the pockets, and then you complete the molecule. You can do that too. We've worked on this optimal control Schrödinger bridge problem. So this is a problem where you take a particular molecule and you want to get it from one metastable state into another metastable state, or maybe even undergo a chemical reaction. And so that is, you will never, if you try to do this in your computer and wait, you'll never see it because these barriers, the energy barriers are too high, and your simulation is too slow. And so you need to help it along a little bit. And so now you can consider this as a control problem where you apply a little artificial force in your computer to every atom, and then you make it move over the energy barrier to the other side. And then when you compute things, physical quantities, you then have to, of course, compensate for the fact that you added this force. But it speeds up your problem tremendously. And you just can think of this as a control or reinforcement learning problem. And here you see a little video of, there's the potential energy as it goes up, as it's trying to find its way on this free energy surface. On the left upper corner there, the blue is low, and the other ones are high free energy. Yellow is high free energy. And the state of the molecule, as it's being driven from one state to the other one, you can see there at the top. And so we've been driving it from one local minima in the free energy surface to another one. So this is the last topic, but I think I'm running out of time a little bit, right? How much time? 5 minutes. So this is the last topic, something I did more recently with the student Jacob Dijkman and a whole bunch of other physicists and machine learning people. So here the idea is if I give you, let's say, a particular, if I give you a whole bunch of data of a liquid, or let's say molecular simulation data of atoms in a liquid or a gas interacting, and I give you an external potential with which this liquid or gas interacts. So let's say you're trying to figure out how carbon dioxide relaxes onto metal organic framework or something like that. Then you have to solve that equation, which is called the grand canonical potential, which has a free energy for the internal degrees of freedom, which determine the properties of that liquid, of that gas, how it behaves basically. And then the interaction of the liquid with the sort of external potentials is given by rho times V. But you don't know what this free energy of these internal degrees of freedom is. You have no idea because physicists have been trying to write down equations for it, but they never turn into some very accurate model, and that's why this is sort of a method that's not being used a lot by physicists or chemists. So what we did is we turned this into an actual machine learning model. We did lots of simulations, molecular dynamics simulations, and we could then sort of take these molecular dynamics simulations, the outcome of them, we push them through a neural net, we compute the free energy with that, and then we do 2 times outer differentiation to get the 2-point correlation functions, and those we could match to data from the molecular simulations. And then once we have trained this whole thing, we can then run it. And if you run it, this is in 1 dimension. We can now already do this in 3 dimensions. So you see the red one is ground truth, density profile for a 1-dimensional system. And then the blue line is the algorithm as it converges to try to reproduce this density profile. And I just want to point out again that there's many methods in this field where physicists have tried to write down equations with some parameters by doing expansions and stuff like that. It never really worked. So here, the revolution is to not try to do that, just learn the actual free energy. It's now a very ugly neural network that has very non-local interactions. Physicists don't like it too much because they look at it and say, I don't know what's going on. It's like a messy thing that I don't understand. But it is very, very accurate. And you can try to then maybe do symbolic extraction or regression again to come up with equations that physicists might, in the end, understand. But as a method to predict the properties or the dynamics of a fluid, this is actually a very good method. Okay, so then I'll come to the end. So I feel that we're at the cusp, if you wish, of a new age. So we've been naming, the ages in which we live by the materials that we use, and of course, those define, our state of development in some sense. You could argue we went from stone to bronze to iron, and now we're in the plastic age. And I think we're moving into a materials on demand age. You just type a material that you want with certain properties, and there's going to be some method that will deliver that particular material to you in the form of in a computer. And I think why this is such an exciting field and why I think this institute, this IX Institute, is very timely, is that there's many things which are coming together right now. We have the sciences, computer science, the computational chemistry, biology, and quantum matter physics, which are already very matured fields. But less mature but very fast progressing are computational science, machine learning, and quantum computing. Those are methods that are currently evolving very quickly. And they are starting to work together now. And that's why, and that's only quite recent. We've seen only a few highlights and successes, which I hope I highlighted in this talk. But this, of course, is just the beginning of something much bigger that's happening. And the other part is that this is pulled by very important applications in the energy transition, in health, new drugs, for instance, against resistant bacteria, and in sustainability, let's say carbon capture applications. So there's a lot of pull from these societally very important problems that we need to solve to work on this. So my view of that is that we really need a search engine. A search engine where you say, I need a molecule that has these properties, it binds to this disease vector, and it's not toxic, etc. So you can just put a whole bunch of things in there. And then something happens under the hood, and you get a whole bunch of these materials. They're fully characterized, in your computer. Maybe they've even been sent to a robotic lab and being synthesized and being characterized and all that, and then it gets back to you. The chemist looks at them, says, "Yeah, maybe it's not actually what I wanted. I want, You update your input, your search term, and you go again." I think we can do this. It won't be tomorrow, but it will maybe in 10 years. We can actually build this thing. And that's, of course, what CuspAI is all about, which is this new startup is actually trying to build this particular search engine. So then to end, I've talked about the deep connection between AI and the natural sciences. And I think free energy is kind of the bridge between them. So that's the concept which bridges very interestingly between these two fields. I think machine learning is a massive new hammer for computational scientists that they soon will not be able to ignore. But in reverse, I think the natural sciences, and in particular physics and mathematics, are also delivering very interesting new concepts to improve our machine learning algorithms. And probably most exciting to me is that this is actually starting to make an impact in health and sustainability through new drugs and materials, and that's something that we will dearly need in the next 50 years or so. I'll end there. Thank you.
Thank you very much, Max, for the beautiful talk. Very inspiring, a lot of things. So please, questions.
So you've hinted at this in your talk that a lot of the advances were enabled by the exponential growth in computability and Moore's law and so on. So what is your prediction how this is going to continue, and how can we make these kinds of advances in AI sustainable as we require more and more compute?
Yeah, that's a very difficult question, I think. So to me, I'm slightly, so many people say we should just make more efficient AI algorithms, but I view this as basically a bigger refrigerator. So when I went to the US and I lived there, my refrigerator suddenly was twice as large. And of course, in the first week, it was half full, but then after a month, it was full, right? And so that's going to happen here too. If you give me more efficient chips and more efficient algorithms, we'll max out on them because it's the economics that's really driving this. And so the only way, in my view, to do this is to tax pollution, because it's the fair thing to do. I mean, future generations have to clean up after our mess already. And so if we can sort of try to compute what an extra kilowatt hour of energy will cost a future generation to clean up, or all the disasters it's starting to now create in countries like Africa and continents like Africa, then I think we need to start taxing very seriously on pollution. I think that's really it's all economics in my view. It's unstoppable, right? It's like, I didn't sign this petition that said, let's stop for 6 months, because it's not going to happen. It's not going to happen because it's all, I view industry as a big machine that, you can try to, regulate, I think, and it's possible to regulate, but if you just ask them to please do something, it's like if their competitor isn't doing it, they'll have a disadvantage and they won't do it. So the only way is regulate this and tax it, in my view. Otherwise, it's not going to work. Of course, my view is that let's use AI to also try to reverse some of that, right? I know we will need carbon capture in the future. It's impossible to solve the climate crisis without it, because we already need to take an enormous amount of carbon dioxide that's in the air out of the air after 2050. So it's better to start now to develop that technology so that by 2050 we are ready. And to me, there's maybe one silver lining to all of this. If humanity puts their mind on something, although they always start too late somehow. We saw this in COVID. It has to be, in their face in some sense before they do anything. But when they do, they can go very fast. And so you can, for instance, see this also with the photovoltaics, like solar cells. They're way cheaper. They're on their own Moore's law, which is faster than anyone could ever predict. So if you can get rid of some of the uncertainty in terms of investments, if big oil starts to understand this is the future, they need to do their investments in carbon capture and not in drilling for oil. If that uncertainty, this financial uncertainty goes away, then they will all be racing towards being the first and best in class for capturing carbon and turning that into synthetic fuels. And that's really what we need to do, which is drive the cost down, remove this uncertainty, and get all big oil companies on board to go there. And then I think it can go fast. So I do have hope, but it's a race against the clock for sure.
Thanks. I was wondering with the free energy functionals you learnt in your last example, how generalizable are they? Do you have to do an MD simulation for if you want to use a different substrate or whatever? You have to redo this whole thing again?
I am so happy you asked me that. So the first thing is if you fix the Lennard-Jones potential parameters, then it will generalize across all fluids that are described by that particular Lennard-Jones potential. So, particularly the method that we developed here it's trained irrespective of the external potential. So it's like you have this fluid and it could sit in one potential, another potential, or interact with one molecule system or another molecule system. During training, we developed a method that doesn't even see these external potentials. It just reasons about its own internal sort of properties. And so it should, right? If you do it right, this potential that you're trying to learn is really about, the internal properties of the liquid. It's not about how that interacts with the external potentials. That should be given once you know how it internally works. And so we've seen that, if you keep the parameters of the Lennard-Jones potential constant, and you train this functional, then it will work for every external field that you apply to it. And that generalization is very extreme, right? You train it only on bulk, and then you put a potential with huge, very high, spikes in it, and it will just perfectly generalize to that. Now, of course, there are, people do want to change parameters in their liquid, right? So it's, if you do a molecular simulation, you change the parameters, then you will have to retrain. But you could even imagine where you have a sort of a bigger foundation model which is trained on a whole bunch of these, and you fine-tune maybe on separate ones. And so currently people are trying to train foundation models for machine learning force field. People said that's not possible, but it's pretty possible. It's working quite well already. And so here you could also imagine you train one functional across many different fluids, and then you just fine-tune it to the one that you're interested in.
Okay, thanks.
Hi, hello. I have a couple of questions. I'm not completely from this field, so I hope they are not trivial. So you spoke about the fact that you're trying to build a foundational model for chemistry similar to maze. Now, I'm not a chemist, but graph neural network, because I assume that you're going to use a graph neural network, should not scale super well. And so I was curious about what kind of problems you can actually tackle with this technique and what problems you cannot tackle with this technique. And then regarding the Aurora...
Should we do one at a time? Because my memory is very, very short. And when you say it doesn't scale very well, so first of all, it's Meta that's developing this, and we are working with them. Now, we have been working on mostly, some equivariance models, and they were all indeed graph neural nets. So when you say they don't scale very well, what do you precisely mean? Because I think
with the size of the graph for the training.
But okay, let's say you have like n layers, right? So you need to go through n levels of computations. That's probably not what you mean. The size of the graph, at every one layer, every neighbor exchange one message to another one. Mm-hmm. That's, proportional to the number of nodes. I mean, you're not connecting every node to every other node. You're connecting every node to a local neighborhood of those
But
nodes.
the local neighborhood could be big, no?
Well, it doesn't have to be big, because if you have many sort of layers, then you can sort of pass information from far away iteratively to other places. So it's kind of the number of iterations, that's the number of layers in your neural net, times sort of the environment, the locality of your update. I would say that scales order n, which is what you need, times a constant, which is the size of your neighborhood and the number of layers. I think that's what you need. I think you're not going to get much better than that.
Okay, so it's fine, basically.
Well, I'm not sure it's fine. It's still, you could, every one of those computations might still be too slow for you, and so there is still a trade-off, making sure that every one of those computations is very fast. And speed is very important, so there's always going to be this trade-off between accuracy and computational complexity. But I would say that it's fine in the sense that it scales with the right order, in some sense.
And second one, regarding Aurora, like, have you tested how the model works against distributional shift of the data?
Yeah.
And
yeah, good point. So of course, this is we did do that, and it's pretty good. And of course, the more data you have, the better it is. But there's no guarantees here, in the sense that I do agree in some sense that numerical solvers, they have a lot more prior knowledge in them about the actual PDE, which we completely lack. And so I would be reluctant to apply these, let's say, to predict climate change, because the actual CO2 concentrations in the air will change, and the model has never seen these things, and it might go off the rails. So that's why uncertainty prediction or uncertainty awareness in these models is also very important, which is something I'm also working on. But there is a trade-off again. The trade-off is as you make them more black box and apply less physics priors into these models, they will have a harder time generalizing outside of distribution, out of distribution. But they are fast, right? And on the other hand, if you apply, if you put in a lot of physics laws, they might slow down because of that. But then they probably generalize better.
okay, so right now there is a compromise between. One is to find a compromise between the two techniques.
It's always a compromise, but it's not so bad in generalization, turns out. It's surprisingly good, but I don't have any guarantees for you, so that's maybe the issue.
Thank you.
Oh, thank you very much. Well, okay, thank you. Yeah, this is a very general question about AI and science. I really like how you were able to, make this talk about constraining the AI training with what happens in physics, back and forth. And then I was saying when I see that you can predict the weather so well, and you can do it based on data that doesn't necessarily have to be physics. So my question is, when we can now use AI, to, in a way, compensate with our deficiencies in physics understanding,
Yes.
do you think this is going to, in a way, hamper our way to develop science based on observation? Because of the compensation that we're going to have with AI that doesn't necessarily has to translate with the real physics?
Well, I think it figures out something. Okay, so what is physics, right? So physics is also just a very compressed way to see the patterns that are in the data. And it's been surprisingly successful in compressing them down to a few equations that fit on a single T-shirt in some sense, right? So that's the miracle of modern physics. But you could say, even if you look at the Navier-Stokes equation, it's short, but it's approximate. So I would argue that there's higher order terms there. You can keep on adding higher order terms for a very long time. The equation becomes less interpretable, more ugly, perhaps, but more and more accurate and more computationally demanding. Something like that is happening inside this neural network. It's like it's seeing all these patterns in some kind of combination. It's very uninterpretable for a human, but it's trying to model the physics in some sense. It's trying to compress what it's seeing in the data into some kind of lower dimensional compressed representation. And as you start to compress things, there is understanding that comes out of it. It's just that the representation is quite uninterpretable for humans. But that means, maybe at some point there will be a paradigm shift when we let go of this kind of desire to understand ourselves precisely what's going on. And the example that I always use is if you go to the doctor and you feel you have a horrible disease, and the doctor says, well, I have these two methods for you. One method is, I know perfectly what's going on, but it's only 60% of the time it captures your disease. And there's this other black box magic that's going on, like a deep neural net, but is 99% correct, right? Which one would you pick, right? You pick the black box one because you want to get better, right? And so I think, you know, there might be use cases where that's the right thing to do, not try to understand ourselves. But you could also try to backtrack from that and say, okay, what are the dominant effects here, and can I extract them again from the neural network? So as a human, with my limited brain, I can at least understand the dominant things that are happening in this mapping.
Yeah. Okay. Yeah. Thank you.
All right.
Let's thank